Okay. Okay. So, the next question that we got on the menu today is what's the formula for instantaneous rate of change? Instantaneous rate of change is often referred to as IROC, because I like rock music. Yeah. So I do rock out sometimes. IROC. Another way to say this is the slope at a given point. Point on a function. Meaning, like, let's say we have a parabola like this. We know that, over here on the parabola, the slope is going to be like that. At the very tippity top, the slope is going to be, well, 0. It's going to be flat. And down here, the slope is going to be, more negative. These are just the IROC values, is the slope at a certain point in time. Okay, the formula for the instantaneous rate of change, well, how would we find slope at a very, very specific point in time? Well, the typical slope equation, slope, is equal to rise over run, which is really just change in the y value divided by the change in the x value, which is the same as y2 minus y1, the second y value minus the first y value, and you do the same with the x values, x2 minus x1. Okay, now x is going to be like, we have our typical xy axes. And the bigger the difference between x's, the more of the function that you're actually going to be incorporating. So you want to get the difference between x2 and x1 to be as small as possible. Okay, so try to minimize difference between x2 and x1. So imagine that we had a little something like this. Okay, we want to be like taking limits, right? And we know that y, let's say y is going to be a function of x. Okay, to minimize the difference between them, let's say for x1, we just set that equal to x, and x2, because we want that to just be barely bigger than x1, we can just make this x plus h, whoops, not b, h, and then like have h approach 0. And the smaller and smaller that h gets, the better and better, or the more accurate our slope calculation will be at that particular point in time. Okay, so we can actually sub these into our slope equation, but have a limit so that h approaches 0. And that's just to signify that we're trying to minimize the difference between x2 and x1, given that we define x2 and x1 this way. So the limit as h approaches 0 for, let's do the bottom first. So it's x2 minus x1, so that's x plus h, that's x2, barely more than x1, and x1, well, that's just x, plus, whoops, not plus, minus x. On the upstairs, well, it's gonna, we know that y is a function of x, so it's just gonna be like the result of x2, which is just x plus h, minus the function when we input x1, so minus f of x. If you look closely, on the bottom, on the downstairs of this function, of this limit, we can see that we have a negative x and a positive x. They neutralize each other, and we get limit of h approaches 0 of f of x plus h minus f of x, all divided by, well, the x's neutralize each other, so it's just h. and h is approaching 0. So this is actually the first principles definition of a derivative. I think, you know, no one knows exactly who the first person to come up with this was, but it's either Isaac Newton or Leibniz, one of those real smart guys from way back in the day. They figured out this definition of a derivative, and that will tell you the instantaneous rate of change. If you were to sub in a function for f of x, you would get the derivative of it, and you could try that out if you'd like. And the derivative is just a function that tells you the slope at a certain point on the graph. Okay, so yeah, and I guess they gave some examples of taking derivatives, and this like first principles definition of a derivative is always going to be right. So they got some examples here, and if you run it through this limit, you will see that the h on the bottom divides itself out, and some of the other h's, well, you can just direct sub h equals 0, and you should get the derivative. I mean, it will always work out, I promise. But yeah, answer is going really above and beyond if it's just asking for the formula. First principles formula is like this. But as you get more and more practice, you're going to use the first principles equation less and less, and you're going to rely more on your already studied and already known derivative equations. Okay, so yeah, you can just see some examples here. So the above solution is good.